In this lecture, we are going to design a single cycle data path for data processing instruction. In the previous lecture, we have seen how to design the data path for store and load instruction. Now we are going to do it for data processing instruction. So first we will see the instruction encoding or binary encoding for data processing instruction. So data processing instruction example is add, or, etc., sub, etc. So in the case of data processing instruction, what you are going to do is you are going to say, for example, we'll take add, you are going to add two numbers, right? So in the case of data processing instruction, you can give the first number here. You can configure the first operand here. So this is known as a first operand register, so bit number 16 to 19. In the case of load and store, this bit number 16 to 19 was representing the offset address for load and store, but here in data processing instruction, bit number 16 to 19 is used for representing the register holding the first operand. So that is known as the first operand register, right? Then second, for holding the second operand, you can have two options. First one, you can give the second operand directly as an immediate value, 8-bit immediate value, or you can store the second operand in another register known as RM, that is the second operand register, right? So first operand always should be in Rn. Second operand you can give it as an immediate value. Immediate value means directly you are giving the value in the instruction itself. So if you want to add 1 and 2, 1 can be given as a first operand, 2 can be directly given here as an 8-bit binary value. So 000010, right? So so this is one method. You can give the immediate value 2 directly here, or you can store the 2 in second operand register known as RM, right? So second operand can be given as immediate value, or it can be stored in a second operand register RM. So data processing, in the data processing instruction, so let us take add. So what you are going to do is you are going to add the content of first operand register with the immediate value. In the case of data processing instruction with the immediate addressing, you are adding first operand register with the immediate value, or there is another type of addressing known as register addressing. That is what I told here. So in the case of register addressing, you will be adding the first operand register content with the second operand register. That is known as register addressing. So in register addressing, you are adding the first operand with the content of second operand register. In immediate addressing, you are adding the content of first operand register with the immediate value. So anyway, in the data processing instruction, you are going to perform an operation on the first operand register and the immediate value, or you are performing the operation on first operand register and second operand register. So here you should keep in mind bit number 16 to 19 is used for representing the first operand register. So you are in data processing instruction, you are going to perform an operation on first operand register with immediate value, or first operand register and the second operand register, right? So second operand register will be stored from will be configured in these bits 0 to 3, right? And here immediate value will be 8-bit immediate value. That is what you are going to see. So for the data processing instruction, I told there are two type of addressing. First one is data processing instruction with the immediate addressing. So this is a data path design for data processing instruction with the immediate addressing, right? Immediate addressing, what is the difference? You are performing an operation on first operand and the immediate value, right? So here you can see that it is an 8-bit immediate value. So the block diagram remains almost the same in the case of LDR. In LDR, what you are doing, you are adding the offset address with an immediate value. Here, instead of adding the offset address, you are adding the same bit 16 to 19. It is used for configuring a register. In the content, what will be the content of the register? It will be the first operand, right? So this block diagram is same as the load instruction. Only thing is that here in data processing instruction 16 to 19 is used for configuring the first operand register. Previously it was holding offset address. Here it is containing first operand register. It is a first operand register which is containing the first operand 16 to 19. So the block diagram it is the same, right? But only the representation is changing. Here 16 to 19 it is containing the first operand. So first operand register will be configured by using 16 to 19. Content of that first operand register, that is the actual value. If you are going to add 1 and 2, 1 will be stored in the register configured by using this bit. So you are connecting it to A1. So what will happen? From that register 1 will be read and 1 will be sent out through RD1. So here RD1 will be getting the first operand value. In LDR, RD1 was representing offset value. Here you are getting the first operand through this. Second operand, as it is already discussed, it will be taken through the immediate path by sign extension. But here in data processing instruction, there is a small difference. In the case of load, you are giving 12-bit immediate value. In the data processing instruction, you should give only, you will be getting only 8-bit immediate value. So you need to perform sign extension on 8-bit value. So for that, you are adding one more control line here, known as immediate source, right? So if immediate source is 0, that means you are configuring the 8-bit 8-bit sign extension, right? When the immediate source is when the immediate source is 0, you are performing 8-bit. You can see here when it is 0, it is 0 extending 8 bits. When the immediate source is 1, you are 0 extending 12 bits, right? So 12-bit sign extension will be done for LDR and STR. 8-bit sign extension will be done for data processing. So only difference is that in the data processing instruction, instead of 12-bit immediate value, you will be getting only 8-bit immediate value. So configuring that 8-bit sign extension is done by using IM source. So if IM source is 0, you will perform 8-bit sign extension. If immediate source is 1, you will be performing 12-bit sign extension. So here you are writing IM source as 0. So you will perform 8-bit sign extension. So here you will be getting source B as 8-bit sign extended second operand. Source A will be the first operand, and you need to perform the data processing instruction here. So in the load instruction, you are performing only the add, because you need to add base address with immediate. But here in data processing instruction, you can perform add, subtract, or etc. So that operation of the ALU is controlled by ALU control signal. 4 operations you can perform. So ALU control signal will be of 2 bits. So these are the operations you can perform. When the ALU control signal is 0 0, you will perform add. 0 1, you will perform subtract. 1 0, you will perform AND. 1 1, you will perform OR. Right? So by configuring 2 bits of ALU control, you can perform add, subtract, and or OR. So by configuring these 2 bits of ALU control, you will be configuring the operation here, and based on the operation, certain flags will be set. Which are the flags you are setting? You will be setting 0 flag, negative flag, carry flag, or overflow flag. So for setting those 4 flags, you are using this signal ALU flags 0 to 3. So ALU flags, 4 bits are there. 4 bits are used for setting for clearing these 4 flags. Right? So based on the arithmetic or logical operation, you will be performing or you will be setting or clearing the flags by the ALU. So ALU will be setting the flags. So ALU will be generating this control signal. Right? But ALU control is generated by the control unit. It is given as an input to ALU. ALU flags will be generated as output from the ALU. Right? So you got the first operand here, 8-bit sign extended value here, and you are performing the addition here. So ALU control should be 0 0 for performing the addition, and corresponding flag will be set. Then ALU result, that is the result of operation, you need to store it in the data memory. Which register you need to store? In the destination register. Right? So in the immediate addressing mode, you are adding the first operand stored in Rn with the 8-bit immediate value. You are storing Rn content with this, and the you are adding these two. The resultant value you should store in the destination register specified by bit number 12 to 15. In LDR also, bit number 12 to 15 was destination itself. In data processing, you are adding the content of first operand in Rn with the immediate 8-bit immediate value, right? So you are performing the data processing on these two, and the destination you should store here. So for storing that in data, you are storing it in the register. So how will you do that? The ALU result will be holding the register, the processed value. That processed value you need to store it into, say, whichever register it is. Right? So how will you configure the register? Bit number 12 to 15. Bit number 12 to 15 is used for configuring the destination value, so that it is already connected. In LDR also it is there. So bit number 12 to 15 is used for configuring the register value for write operation. Right? So to this register you are going to write the ALU result. Previously what you have done, you were writing the read value to this register in LDR, but now the difference is that you are going to write, that is why it is shown in this black color. Wherever this black color is shown, that is a current execution. So the ALU result should be written to the destination register configured by A3. So that is why a line is taken from ALU register, ALU result, and one more additional multiplexer is provided here. Right? So if the multiplexer is selecting a control input is 0, so that control input is memory to register. So in the case of data processing instruction, memory to register input will be 0. That means instead of selecting the read data output and writing into the register, you are taking the ALU result. By configuring this as 0, ALU result will be available in the multiplexer output, that is known as a result. That result will be written on to the file register. So that is why that is connected to the write port of file register. And which file register you need to write, that is configured by the destination bit, that is destination register bits, bit number 12 to 15. So 12 to 15 is connected to A3. The data which has to be written is connected to W3. This data you need to write in the file register. So for writing the file register, you need to make register write as 1. So write enable will be 1, right? Then you will be giving the clock. So in the rising edge of the clock, whatever data you have given in W3 will be written to the register specified by bit number 12 to 15. So that write process will happen in the rising edge of the clock. Right? So for the data processing instruction, the difference between LDR and data processing is that in LDR you are writing the read data output from the data memory to the register, right? That is in LDR. But in data processing instruction, instead of writing the read data, that is the output of data memory, you need to write the output of the ALU result. You need to write the output of ALU. That data should be written to a register specified by RD, right? So in the data processing instruction, you need to make memory to register control signal as 0 for selecting this ALU result as input. Then ALU control should be selected based on what operation. If it is 0 0, it will perform add, 0 1 it will perform sub, like that. Then IM source should be 0 in order to perform 8-bit sign extension. Previously in LDR operation, this IM source was 1, so that it will perform 12-bit sign extension. Here IM source should be 0 in order to perform 8-bit sign extension. Then register write signal should be 1 in order to give the write enable. Then only whatever data you are getting in the ALU result will be written onto the register. So register write enable should be 1. Finally you should give the clock, right? Then PC source will be used for selecting the next instruction, that is it can select PC plus 4 or this you can do as shown in LDR. So that is regarding the immediate addressing mode data processing instruction. Then next one is data processing instruction with register addressing mode. So in the register address, in the immediate addressing mode, what I told, the first operand register, if you are performing say example add, so first operand register will be added with the immediate value. But now we are going to see data processing instruction with the register addressing. So here first operand register will be added with the second operand which is stored in RM. You will be adding RM and RN. This is a first operand register. This is a second operand register. So in register addressing mode, you are going to add RN with RM. So that is what you are going to do here. So this was immediate addressing. You are adding first operand with the immediate value. In register addressing, so this is data processing instruction with register addressing. In register addressing, you are adding first operand register with the second operand register, right? So for doing that, the first operand register is already specified here, 16 to 19. So you are getting the output of first operand register here. To that, instead of adding the immediate value, you need to add the second operand register, and second operand register is specified by bit number 0 to 3. So second operand is specified by 0 to 3. So you can see here 0 to 3 should be connected to the RD. So RD1 will be getting the first operand output. RD2 you should get the second operand output. So for getting RD2 second operand, you are incorporating one more multiplexer here. Previously the destination register bit number 12 to 13 you are connecting to A3 and A2 directly. You can see bit number 12 to 13 you are connecting to both. That means A2 and A3 both will be getting the will be configuring the destination register, and since you are performing the write operation, it will write. But here what you are adding is that you are adding one more multiplexer here, because here I need to perform read as well as write. Why? I am going to read the second operand through A2. I am going to write the destination in A3. Previously it was not like that, right? So first operand will be going through 16 to 19 to A1. Second operand second operand register you should connect it to A2. So the second operand register, in order to read, you are using one more multiplexer here, right? So in order to incorporate all the operation, so if the register source control bit is 0, you can select the second operand and you can give it here. If register source is 1, you will be selecting this one as the input, because in the load operation you need to connect this as the say destination register. Right, and the store operation it should be like that. So here my aim is to connect the second operand to R2. So I am using a multiplexer here. If the value of that multiplexer, the control line is 0, you can connect the second operand to R2. Right, if you want to connect this destination register bits to R2, you can give 1. But here, since I am performing data processing instruction on register addressing, first operand will be connected to R1, second operand you are connecting to R2 using this multiplexer. So register source should be 0, you are connecting it like this. right? Then so the first operand value will be getting here, second operand value will be getting here, and in order to incorporate the previous immediate addressing mode feature also, you are adding the second multiplexer here. So if, and the control signal is ALU 0. So if ALU source is 0, you will be sending the second operand. If ALU source is 1, you will be sending the immediate value, right? 8-bit sign extended immediate value. So here for data processing instruction with register addressing, you are adding two multiplexers. So this multiplexer is used for selecting the second operand like this, right? You can select the second operand. Second operand is configured by these 4 bits. So register source is 0, that means second operand will be connected to R2, right? So you are reading the first operand in R1, second operand in R2. So first operand will be given as source A, second operand should be given to source B. So in order to incorporate both register addressing and immediate addressing, you are adding one more multiplexer here, and if the multiplexer control bit is 0, then you will be sending the second operand. If the multiplexer control bit is 1, you will be sending the immediate value. So in this case, since you are using register addressing, you need to give ALU source as 0. So the second operand will be sent to ALU. The first operand will be sent to first input, second operand will be sent to second input, and the result you will be getting here, right? That result you can store it in the destination register as already told here, right? So you are incorporating two muxes here. This is for selecting the second operand to the input of file register. This is used for selecting the second operand or immediate value to the source B, right? Remaining all the other things remains the same, because source operation will be the storing. In the case of data processing, the result will be available here based on the operation which you are configuring in ALU control. Will be getting the result here. That result will be coming here. Memory to register is 0, so that register will be going through this path, and it will be stored on the destination file register. Destination file register is configured by bit number 12 to 15. So you are adding two more additional multiplexers. And in data processing with register addressing, what all control signals you need to keep in mind? Register source control signal should be 0 in order to configure the second operand to the input of A2. Register source should be 0, right? Register write should be 1, because the destination you need to write into A3. Then clock you should give. Then IM source should be 0 as you told before. Then ALU source should be 0. 0 means you are taking the second operand second operand data as a source B. So ALU source should be 0. You are not taking immediate value. You take the second operand from the register. So it is 0. ALU control should be based on your operation. If it is add, it should be 0. Then based on that, ALU flags will be set by the ALU, right? Then here memory to register should be 0. So you will be selecting this path and it will be written. And this memory write and clock, memory write should be 0, because you are not writing anything to data memory. Since you are not writing anything here, it should be 0. So you need to configure register source as 0, register write as 1, IM source as 0, ALU source as 0, ALU control based on the operation, memory write 0, memory to register 0. So these are the these are the control signals you need to generate for data processing instruction.